Go ahead and get started. So we went over last time, if you remember, we're going to go ahead and just recall this triangle sum theorem, where we said that the sum of interior angles is 180 degrees. That's all the sums inside of a triangle. Now, all the interior angles of a triangle are more than zero, but less than 180. And that's just particularly applying to a triangle. Um, we were able to prove this by drawing, if you guys recall, the parallel line. We were dealing about parallel lines and the angles. Parallel line that was directly perpendicular to the segment, or to the segment that's created by angle y and z, and that same line was that was perpendicular here. I mean, not perpendicular, parallel here, was also parallel to a segment here. And we were able to find that not only we were able to see that if we created another line that goes directly through the side where angle y and angle x are, we can see that that by alternate interior angles, these two were congruent to each other. And if we create another segment or another line, that is our transverse, that goes through our angles x and z, or that side that our angles x and z are, we were able to see that uh, z is also present there as well. So z is also present here, and the measurement is present here. So we've had the measurement of z here, we had the measurement of y, and we were able to see that all these angles had the sum of 180 degrees because they were a straight angle, and they were three adjacent angles. Um, Therefore, the side or the sides are next to each other, and we have a sum of interior angles, which gives us to 180 degrees. Okay, so we were able to prove that last time, just to recall. We're going to go ahead and now apply that idea to also interior angles, but not only in a triangle, but also to any polygon. So I want you to think for yourselves, how can we determine the sum of interior angles of any polygon? Not just only a triangle, but any shape that we have. Doesn't mean that it has to be regular. Regular means that all angles are the same measurement. Um, but in this case, we have odd shapes, but we do have a special case of being uh, not um, a regular shape in this case. All right, so let's go on. Let's create a table. And we already did our first triangle, our first shape. What's a triangle? We're going to go ahead and classify their sides, uh, and the number of triangles inside, and the sum of interior angle measurements. So obviously the first one that we have was a triangle. We figured out that a triangle has three sides, and the number of triangles, well, it's a triangle itself. So there's only one. So what happens? We're going to go ahead and start seeing patterns where we are able to see that by the number of triangles, we're going to go ahead and multiply it by 180 degrees, and it's going to give me the result of the sum of interior angles, right? So let's go ahead and do now the same to a quadrilateral. How do we see the number of sides of this shape? Well, the number of sides of the shape itself, it says quadrilateral. So we have 4 sides. Now the number of triangles that we have here, we're going to go ahead and pick one vertex. That from there, we're going to go ahead and um, draw several lines that are going to cut our shape into several segments. Let me go ahead and see if I can change this very quickly. Perfect. Okay, so from here, I'm going to go ahead and choose this vertex that I'm going to go ahead and start with. And it's going to then end up in a second vertex. Vertex are the the corners of our shape, right? Now here, I have a quadrilateral. It looks like a trapezoid. It can be any type of quadrilateral, not necessarily trapezoid. I've only selected one initial vertex, and I then connect it to its next vertex. I can do the same for its initial vertex and connect it to the other vertex or the other vertices. Um, but again, we only create two triangles. So what's going to happen here? I'm going to go ahead and fill up my table. Number of triangles created. Well, here I have one. I have two. Therefore, we have two triangles that are created. What's going to happen? We're going to go ahead and then multiply by the number of triangles that we have, which is 2, by 180. Well, if we multiply 2 times 180, our new sum of interior angles would be 360 degrees. And we can go ahead and do our parallines to each of the sides and then continue to apply the same theorem that we did as with our triangle sum theorem. But here with this table, we're able to see that because we have two triangles, we multiply it by 180 degrees and it gives us 360 degrees. So the measurement of the sum of interior angles of a quadrilateral is then 360 degrees. Doesn't matter if it's a square, if it's a rectangle, as long as it's a quadrilateral that does not cave in, meaning that there's no side that goes in somehow like this, but that would not be a quadrilateral then, would be considered to be applying to this row. All right, so that is a quadrilateral. All right, let's go ahead and move on to our next shape. Let's see, let's try now pentagon. Okay, let's go ahead and see. We're going to go ahead and start from one vertex. So I'm going to go ahead and choose this top vertex. Let's see, so from this vertex, I can go from this next vertex, this next vertex, this next vertex, and this last vertex. Now, what do you notice? Well, we create 1, 2, 3, 1, 2, 3 triangles. So let's go ahead and write that information out now. Number of sides, well, it's a pentagon, so it's 5. Oops. Number of triangles, here's my first triangle, second triangle, and third triangle. So I have 3 triangles. Therefore, let's go ahead and apply our beautiful little formula here. So we multiply by 3 times 180 degrees equals 100 and, wait, not 180. I was trying to copy the same as on top, 540, 540 degrees. So the sum of interior angles of a pentagon is 540. All right. So notice that we have 3 triangles. So we can apply the same strategy or the same to each of these triangles that we did with the triangle sum theorem and draw our pentagon if you want, our parallel lines if you wanted to, it'll still give us the same result. All right, so this is a pentagon. Let's go ahead and try the next shape. This is a hexagon. Let's go ahead and do, let's see, let me go ahead and choose, pink. Here I go. I'm going to go ahead and choose this vertex. You can choose either or, as long as you're able to connect the other vertices, but you start only from one vertex. All right. And the last one. So we created, let's see how many triangles. In this case, 1, 2, 3, and 4. So how many sides? We have 6 sides and 4 triangles. 4 times 180. In this case, it should give us 720 degrees. 720 degrees. So now from looking at this information, look at the table, look at the number of sides, not so much on the shape because the shape already tells you already by the number of sides, but also by the number of triangles. I want you to look at it close. If you want to pause this video and analyze our table that we've created with that information. Once you have created your conclusion of what is it that you notice between the number of sides and the number of triangles that are within the shape, um, go ahead and write that information out in the next slide. Where in the chat box, in this case where there's no chat box, you're going to go ahead and tell me what patterns you identify about the sum of interior angles of a polygon. So notice that we were given the table. Let me go back. We have now the number of sides of triangles, number of sides, and the number of triangles. Notice what do you identify here? Go ahead and write that out in the next slide. I know it says chat box, but it's going to be on the slide since we are doing this asynchronously. I hope you guys were able to identify some patterns or a pattern happening, and mostly about particularly happening between the number of sides and the number of triangles within um, a, a polygon. So if you notice, let me go back to my table. I have a number of sides, right? So for every side that I have what appears to be two less of triangles. So for example, my first number of sides that I had were 3. Notice that I had 1 triangle. So it appears to be 2 less. Let me go ahead and see if it's true for the next one. So 4 sides minus 2 gives us 2. Pentagon, 5 sides minus 2 gives us 3. 6 sides minus 2 gives us 4. So here, if you were able to identify that it will appear to be 2 less triangles in comparison to the number of sides of the polygon, then you were in the correct track. All right, so let's go ahead and move on to our first example. So before we move on to our first example, we're going to go ahead and now be introduced to our polygon angle sum theorem. And it states that the sum of the measures of the interior angles of a convex polygon with n sides, meaning that we don't know the number of sides, but we know that it's n values, is going to be represented by our little formula that we were using already, n, which is the number of sides, minus 2. Notice that it's 2 less, times 180 degrees, which is what we were doing already on our beautiful table. Here, convex means that it's not caving in. So notice that this shape goes into the polygon. These two sides go into, they cave in. Convex meaning that all the sides or all the vertices are outside, directly outside of our polygon. And here I have examples. For example, here I have when n equals 3, we have a triangle. When n equals 4, we have a quadrilateral. N equals 5, it's a pentagon. N equals 6, it's a hexagon. N equals 7, it's a heptagon. And n equals 8, it's an octagon, and so on and so forth. It just depends on whatever number of sides. So we have an octagon, we have n to be equal to 8. We would then, if you want to go ahead and draw each of the triangles to see how many triangles we have, you'll notice that you'll have 2 less, right? So you have 1, 2, 3, 4, 5, and the last one, let's see, 1, 2, 3, 4, 5, and 6. There you go, 6 triangles in there. All right, if you don't have this in your notes, please go ahead and copy this down so you can have it. You may pause the video, of course, and resume. Okay, so here we go. Let's go ahead and go on to our first example now. Our first example says that we I have to determine the unknown interior angle measure of a convex octagon in which the measure of 7 other angles have a sum of 995 degrees. Now, notice that there's a lot of information that's given here. However, we don't have the image in front of us of the octagon and the other angles. However, from this information, we're going to go ahead and underline everything that's given. So let's go ahead and start with, we have to determine, right, the unknown interior angle measure. So we have to find out what the interior angle measurement is of the octagon, which the measures of the 7 other angles have a sum of 995 degrees. So the other 7 angles that we have a sum, right? Have a sum of 995. Now let's go ahead and first draw that beautiful octagon so you guys can see what I'm talking about or what we're discussing. An octagon has 8 sides. So I'm going to go ahead and try my best. 1, 2, let's see, 3, and 4. There you go. It looks like a stop sign. Let's go ahead and imagine that. If you need to, you can go ahead and draw your vertices how we did in the previous example. Let me go ahead and pick this one. And we have this. Let me go ahead and choose a different color. So here we have our first triangle, second triangle, third triangle. We should have 6, just how we did on our previous example. 1, 2, 3, 4, 5, 6, 7. How come I have 7? Now I know why. This one was one whole side. There you go. And like I said, it's not a regular shape, so not all the sides are going to be 1, 2, 3, 4, 5, 6. There you go. Going to be the same length. Okay. So we have 6 triangles inside. So we know we have to multiply that by 180. However, if we were to use our beautiful polygon angle sum theorem, it says that we just need the number of sides and we need to subtract it by 2, and we will then receive the sum of the interior angles inside this polygon. So let's go ahead and do that first. So what is the number of sides of an octagon? Well, we know that octagon has 8 sides. So our first value of n, which is the number of sides, is 8. And it then says that we have to subtract 2 from the total number of sides and multiply that by 180 degrees. Okay, let's go ahead and do that. Let's see, 8 minus 2 times 180 degrees. It's then 6 times 180, which gives us a total, I think it's 1,080. Yep, 1,080 degrees. So the interior angle measure of an octagon is 180 degrees. This number will always be the same if our shape again is convex, right? Meaning that there's no angles shaping it or any vertex existing within the angle, within the shape. Okay, so let's go ahead and now see what else is given. 7 other angles have the sum of 995 degrees. So we already know that we are given that the sum of 7 other angles, I'm going to go ahead and write angles, is 995 degrees. Well, then if we know that 7 other angles are 995, then what we're missing is the measurement of one angle. All right, so let's go ahead and write our little formula for that. So 995, right, plus x, which is that last angle that we're missing, equals its total sum of interior angles, 1080. So 995 plus x, which is that last angle that we're missing, equals to 1080. So let's go ahead and subtract 995, 995. Let's see, x equals, go ahead and subtract 180 minus 995. Let's see what you get. All right, I hope you guys had enough time to solve this. And the answer is, if I'm not wrong, 85 degrees. Yep, the answer is 85 degrees. Let me go ahead and change my tool. 85 degrees. So here, that missing angle that we had, which a measurement we did not know, we now know that that eighth angle that that octagon has measures 85 degrees. All right, let's go ahead and go on to example number 2. Example number 2, we're going to go ahead and determine the unknown angle measures of this pentagon. No measurements are given. Well, actually, measurements are given, but no actual numbers are given. But we are given some physical measurements there. Go ahead and pause this video so you guys can go ahead and copy this down and resume. All right, from the information that we have from the image, we're going to go ahead and first determine what shape do we have. Well, it appears to be a pentagon. 1, 2, 3, 4, 5. 5 sides. What are we going to go ahead and do first? We're going to go ahead and determine the sum of the interior angles first. Since we have a pentagon, which means that we have a polygon of 5 sides, we're going to go ahead and determine that our n is going to equal 5 in this case. So n minus 2 times 180, which is the sum of interior angles, then will give us the value of a pentagon. What's the sum of interior angles? We already calculated that in our table earlier today. We're going to go ahead and do the same here. So we have 5 minus 2 times 180. We have 3 times 180, which gives us 540. Yep, 540 degrees. So we know that whatever these angles are, whatever their measurement is, we know that their total is going to be 540. All right, so let's go ahead and create now our beautiful equation. How do we do that? Well, we have measurements here. Even though they're not physically given, they're just stated by saying that this is a measurement of 90 degrees. Notice that whenever we have that little square, when two sides are meeting or joining, it means that it's 90 degrees. So this is 90 degrees. This is also 90 degrees. And we have two angles that measure x. We don't know what the measurement is, but we know that both of them have the same measurement, which is x, right? No matter what it is, it's going to be the same measurement. All right, so let's go ahead and create that beautiful formula. Let's see, 90 plus x plus 90 plus 90 plus x. So let's go ahead and do 90. I'm going to go ahead and start from the top. Plus x plus 90 plus 90. And the last angle that we have there is x equals 540. All right, from here, we can go ahead and simplify by combining like terms. Our first term that we have 1, 2, 3 90s, and we have, let's see, 2 x's. Okay, let's go ahead and combine that. 90, 90, 90 gives us 270 plus x and x. We have now 2 x's equals 540. All right, let's go ahead and now solve for our value of x. So subtract x, or subtract 290, 270, subtract 270, both sides, to x equals, let's see, borrow 1, 14, to 7, 13, 6, 8. So we have 0, 8, and this is now 4 minus 2, 280. 270, sorry. 7 and 7. For some reason, I thought 8. It's okay, guys. We all make mistakes here. All right. Divide by 2, divide by 2. X will now give us 135. Yep, 135. This means that each angle that we have here inside of our pentagon measures 135 degrees. 135 degrees. Okay, so what do we do here? We added or had the sum of all the angles inside of our polygon, which is a pentagon in this case. And then we created our formula. We made them equal to 540 because 540 is the sum of the total sum of interior angles, meaning that once you add all the angles, we'll have them equal to 540. We have one variable, two sides, which have the same variable, x. We then combine like terms, solve for x, and we were able to determine that measurement for x. Okay, let's go on to the last one. And example number 3. This one is your exit ticket. You're going to go ahead and determine the 4 interior angles of a quadrilateral if you know that the other 3 measures are 89 degrees, 80 degrees, and 104 degrees. So you have to determine the 4th interior angle of the quadrilateral that you have there, knowing 3 measurements already. So go ahead and solve this one as your exit ticket, and this will count as part of your class participation and your notes. If you have any questions, don't hesitate in asking me. Thank you.